it's great to talk to you guys about something that's really passionate to me around IP and optical networking, namely the middle mile and coherent routing. These really are key things in the industry today, and they really make the most of recent investments in access networks, etc., and new applications. And these can only be good for the community in general and our corporate social responsibilities to help everybody. But before I go into that in more detail, for those of you that don't know Ribbon, sort of with a heritage from Nortel, Genband, Sonus on the voice side, and a recent amalgamation of ECI on the IP optical side, Ribbon has more than 50 years of experience in the telecom business. Today, our headquarters is in Plano in Texas. It's a very nice facility there, but we have facilities all over the world. Currently, our revenue is just under $1 billion US dollars, with just over 3,000 staff and 1,000 customers. I mean, it's a lovely company to work for. I would say a medium-sized telecom firm. So really great fun to work there. And I myself work in the IP side of the house, and I'm responsible for the IP portfolio and the solutions based on it. So enough about me, and let's move on to what we can do at Ribbon. So as a company, we supply everybody you can imagine. So all of the big tier 1s, tier 2s globally have either bits of our voice solution or our IP optical solutions. But we also address cable codes, which are called MSOs in the North American region, and also all of the sort of critical infrastructure and defense type customers we are really, really proud to have as our customers. So a wide diversity of customer base. The one thing on the IP optical side that really, really links all of these customers together is they're all looking to upgrade what I call the middle mile, and more of that in a bit. So, as I mentioned at the start, we have two business streams in Ribbon. The voice business stream, which is focused around taking the old Nortel SBC assets and IMS and moving to more cloud native unified communications and things like robocalling, mitigation, etc. That I'm not going to talk about today. What I am going to talk about today is our IP optical side of the house and how that is now driven by what's needed in the middle mile and how coherent routing is a key part of that. So with all of that prelude, the drum roll, what is the middle mile? So the middle mile sits between the access networks. So we all know what the access networks are. It was DSL in the past. Now it's GPON, EPON, etc., or it's DOCSIS 4 if you're an MSO, or it's a field area network if you're critical infrastructure. Vast amounts of money have been ploughed into access networks over the last 4 or 5 years, with 5G rollout, fiber to the home, smart grid, etc., on the CI side. And on the application side, we see more and more applications looking to take advantage of this access bandwidth. What could go wrong? Well, if we don't look at what's happening to connect those access networks to the applications, you will not get the sort of performance you want or need. So the middle mile is what connects the access network to those core application services, data centers, command and control things. So as such, that middle mile can span anything from a few miles, if you're going to an edge data center, for example, all the way to tens of thousands of kilometers if it's across a submarine link. So really, really quite a big distance. Because we put all this extra money into the access, it's much higher capacity. Clearly, the middle mile needs to scale in terms of bandwidth as we move forwards. But it's not just that. As I mentioned, there's a lot of new applications that have now available. And these require, each application requires a different set of service performance guarantees for it to work properly. Now, for example, high resolution streaming really requires massive amounts of bandwidth moderate amount of availability depending on what you're using it for, and again a moderate amount of latency depending, low latency depending on what you're using it for. If you're a mission critical type business, you don't really need a lot of bandwidth, but you absolutely need guaranteed availability. You absolutely need guaranteed low latency for some of your applications to work. I'll take the extreme of mission critical. If you're talking about fight by wire and defense, it absolutely must stay up. It's no good when you push that button for the tank to take its test fire on the range that nothing happens. So different applications, different service needs. The middle mile has to cope with that. So there are different approaches to achieving this. Firstly, I'm now looking at, say, if the access network was a fiber rollout. So you've got an ONT serving your new access network. And one approach is just to put a 100 gig uplink on the ONT back to the core network. And sure, that's a pretty cheap approach to do it. Unfortunately, as more and more consumers use more and more bandwidth, 100 gigs is not going to be enough. So what do? Do I start with 400 gig? Do I start with multiple 100 gigs? You don't know. So it doesn't allow you to give any sort of forecast tolerance on what that should be. And I did mention about this service performance. Absolutely no way of guaranteeing service performance if you just put a 100 gig uplink in an ONT. You just absolutely can't do it. But that's the simplest form of middle mile. So let's give yourself the option of having a bit more scalable bandwidth and a bit more service awareness. So put a packet network in there, absolutely ideal for being service aware. You can take those packets, you can classify them with QoS, and you can route them across the network to meet their service needs. You can put an optical network in there with optical transport and OLS, and that will take massive amounts of capacity and route it across the network at the lowest cost per bit. If you need more capacity, you just add another wavelength to your optical channel. So a really quite graceful way of scaling the network. And in fact, most middle miles we see today have an IP or packet transport network and an optical network. Unfortunately, most middle miles we see today, these two are like ships in the night, controlled by different departments, run completely independent of each other, which means in reality the OPEX is quite high because they don't understand each other. And actually the CAPEX becomes really quite high to run two separate networks because you're not optimizing the utilization of your networking resources. You're making best effort guesses as to what one layer is doing and what the other is. I mean, in a ludicrous example, and I fully agree this is ludicrous, you could do 1+1 protection in the optical layer, and then you could do 1+1 protection in the IP layer because you didn't know the optical layer did it. And then you're transporting services across this transport network. You can then use application protection across that. So even just in those transport layers, you're reducing your maximum utilization down to about 25%. So if you start to know about what the network resources are doing between the IP layer and the optical layer, you can then up your utilization of your network, which is much more environmentally sound. It allows you to offer new services more quickly. It really allows you to minimize that total cost of ownership of the network. So of course, I'm going to say what you need is an intelligent middle mile where you have a set of networking assets, a network of networking assets comprised of IP functions and optical functions, and you make sure you use the right function at the right time to best meet your service needs and to best meet your cost and transport needs. And to do that, you'll need intelligence in your what used to be called a network management system. is these days called a domain orchestrator or SDN control. That management system must be able to communicate across all those network assets and allow the right network assets to be chosen. But also what comes into play is how can I actually use those network assets in the most effective way? So to go back to that, I looked to the building blocks of this IP optical middle mile. I've already mentioned the routers. The routers are there. They're performing your service awareness. They're able to look at traffic coming in and route it across the network in the way that best suits the performance needs of the service. You next have your open optical line system. Who knows what the O means in OLS? Sometimes it means open, sometimes it means optical. To me, it means open optical line system. Anyway, so this is your optical transport network, transporting data across the network. And then probably you have the most expensive bit of the network is coherent transceivers. These are the optical plug-in units that actually take the signals and actually send the raw power out into the network onto the fiber to actually give you your reach across your fiber. Up until very recently, those transceivers have been associated just with the OLS, and that's where they've been located in optical products. These days, you hear more and more about pluggable optics in routers. The reality is those, as the diagram shows here, these coherent transceivers can sit in both locations, and you can choose what is most appropriate for your needs based on what you require, what your architecture of your network is. And in essence, that is what coherent routing is, and I'll explain a bit more as we go forward. But of course, for all of this work to work efficiently, you actually do need that domain control to really understand how to do the path computation across the network, to monitor the network when it's in place, to make sure that if it's a gaming service you're offering, that a network path is chosen what has the lowest latency across the network. Again, because gamers, for example, are willing to pay for low latency networks. So moving on to an examination or a slightly deeper dive on each of those elements I pulled out around the building blocks. The first is that IP aggregation routing layer. That's clearly got to support multiple interface types, not just the current 1 gig to 10 gig and beyond Ethernet interfaces you get today. There are still lots of legacy services, legacy interfaces out there in those middle miles I mentioned at the start. So you've also got to be able to support SDH, for example, because there are still rucks of SDH in service provider and critical infrastructure business. So you've got to support multiple interface types. I focused on the diagrams before on the fixed wire fiber rollout type access network, but that equally might be a 5G network or a 4G network. Or if you move into, say, critical infrastructure, that might be a LoRa type interface. So this aggregation layer has also got to take all of these different access networks and be able to do something with those to route the traffic across. Now, clearly, depending on where you are in the network, you've got to have the right size box. No good putting a super humongous size box right at the edge of the network. It's not going to be used, very cost inefficient, very environmentally unsound. Similarly, you don't want to put minute boxes in the core of the network because they just aren't good enough to do the job. So you need the right range of form factors. So there's a whole range of routing sizes that fit. And then different operators want different architectures. So you've got to support various network topologies. You know, in what I would call the access aggregation area, ring, chain, mesh are the prevalent types of access network. As you move more into the core of the middle mile, for want of a better word, it's mainly a sort of partial mesh type ring network. And you use a lot of what's called dual homing or multi-homing, where traffic can be sent in multiple directions across the network so you can get protection. Then, of course, to give this ability to adapt and change with change in demand, this network's got to be dynamic. Now, if AWS install a new edge data center, you've got to route traffic there. It's got to be dynamic enough to cope with that. So that's the IP side of the router side, as I mentioned. Then moving on to the coherent transceivers. Well, there are two types of coherent transceivers. One is optimized to maximize performance with constraints on size, power, cost. With these, you get the highest wavelength capacity and reach. And today that reaches 1.2 terabits per wavelength. And you think you can have multiple wavelengths on a fiber, you're talking a vast amount of traffic on a single fiber. But that 1.2 wavelength, 1.2 terabits is for sort of short haul applications. The same sort of capacity reach optimized transceiver can be used. If it's used at 400 gig, you've got thousands upon thousands of kilometers of reach. It's virtually unlimited. And by and large, these capacity reach optimized pluggables are a proprietary technology and don't have standard form factors. It doesn't mean they're not interoperable. I mean, at OFC, Ribbon demonstrated 1.2 terabit interoperability with Cisco, for example. So they can be interoperable. They're just not standards based, and the size and form factor of them is not. The other option, and this is the option we see both in optical devices and also in routers, is pluggable SFPs. These are standard form factors like the QSFP-DD and the QSFP-28. And they're based around open standards like from OIF, OpenZR+, etc. And these are sort of lower power, and they're really performance cost optimized. Today they are at 400 gig. In the future, that we're already looking at 800 gig for these sort of pluggables. Okay, so and what can you do with these? With the fact that you've got these different options? Well, you can see you can have different ways or locations to put the pluggables into the network. What the simplest form is just to plug a transceiver into your routers. And if the reach isn't too far, maybe 100 kilometers, you don't need anything in between. It's just router to router communications. If you don't need to do anything else, that's great, it works. If you need a bit more reach, you can put an OLS system in there to give you the regeneration that you require. However, if you've got a bit more complexity, you can have routers and switches communicate each other using a separate optical transport layer. So this might be that you're trying to multiplex one or more wavelengths together. It might be you're wanting to go 1,000 kilometers. Various reasons for doing it. And you can also have, in this diagram here, you can see there is nothing stopping you having an optical transceiver in the router and an optical transceiver in the optical transport equipment. That's absolutely acceptable. And then finally, we move into sort of a more traditional architecture where we're using an optical transport layer and there's coherent receivers in both. So let's dive into a little bit more of that because it's a really high level thing. But first, we must talk about that OLS because it's pretty much common across all of the solution. So the most important requirement about the OLS is the ability to handle any wavelength from any source, whether that be a router, another optical network from the same vendor, or an alien optical network wavelength from a different vendor. And the OLS will do basic things like add, drop, amplification, monitoring the spectral bands, etc., for shared spectrum type uses. And another important aspect to take into account when looking at coherent routing is the network control. As I mentioned previously, the two domains must be controlled and optimized as seamlessly as possible. With the IP services being at the end of the network, the IP layer and the management system must work together to compute the most efficient route across the network to meet the service demands on a service-by-service basis. So let's look at some use cases around this. In many cases, routers will only need 100 gig interfaces. So that was the sort of case I mentioned previously. And what we have here is we're using the optical transport network to do interface aggregation. So basically, from the routers, you may have a number of different wavelengths, as I mentioned, and you're using the optical transport network to aggregate multiple 100 gig interfaces into a bigger interface to send further across the network. And then the router at the far end can be take a 400 gig interface and take the traffic off that. So you immediately reduce the amount of wavelengths you're consuming in the network. And if the routers happen to be closer to the optical transport equipment, you can use grey optics to achieve that, right? You don't even need to put the optical transceivers into the into the routers. You can use grey optics in routers. Again, reducing the cost massively. It all depends on what architectures the operator has and what their preference is here. The idea is to have the right tool set to allow the network operators to choose the right capabilities for their needs. So in this example, we're just doing pure regen. If we don't need the regen, as I mentioned before, we can just stick with the router-to-router communications, maybe with some OLS in there if we need a little bit more reach. In this case, you're using the optical transport system just to regenerate the 400 gigs, because you will just want to go that much further, maybe thousands of kilometers. So an example of this, you can consolidate these multiple wavelengths and go that sort of distance. So as an example of this, a few weeks ago, or maybe a month or so ago, we did a demonstration, a field trial with a company called Surf, who can connect the Netherlands with the Large Hadron Collider in CERN. And over old fiber, we were able to go a distance of 1.6 kilometers. So 1.6, that'd be nothing. 1,600 kilometers reach for an 800 gig wavelength. So that's quite an impressive proof of how you would use your optical transport network with modern technology to get huge capacities, ultra long distances. And then for short haul type applications, like for DCI, etc., what you're doing here is you're actually just doing, as I said previously, you're consolidating many lower rate interfaces from the routers to transport high capacity data center interconnect across the network. So 800 gig, for example, in this use case. And similarly, you can use those optical transport, optical network to take those interfaces and make them go for a long distance. And again, as I said, at 400 gig, this can go on for thousands of kilometers. No, submarine type length we're talking, if you need to. So with all these different options available, you provide the operator with a toolkit to allow them to build the most efficient middle that's achievable. And at Ribbon, we call this the intelligent middle mile, because you've got all of those IP network resources, all of those optical network resources, all being used in the most intelligent way to meet service performance needs at the lowest TCO. But one should not forget what the end driver for this is. It's not about the network. It's about delivering services. So if you've got a, let's think, for example, say the gaming example, because it puts a lot of constraints on the network, and people are willing to pay. Those really require to be low latency connectivity if you're talking about sort of cloud-based gaming. So when a service is created in the residential home or on the mobile, it's going to be asking for having a low latency connection. Availability, yeah, it's got to be reasonable, but it's not going to be as reasonable. It's not always up. They can take a little bit of outage. And generally the bandwidth is quite high. So as you hit into the IP network, you're going to look for a set of resources that most meet those needs. Now, in terms of low latency, if the data center which houses the game is local, you can probably stay in the IP layer because you're not going to go through too many hops. You're not going to go a huge distance. But if the data center that's housing the game is, say, on another continent, you really are going to want to go onto the optical layer as soon as you possibly can, because optics is the lowest, adds the lowest latency to the network. I mean, that's a pretty ridiculous example. You wouldn't have the games on another continent, but just making the case pretty obvious. So these sort of considerations apply to all network operators in different ways. So the sort of areas where optimizing that middle mile becomes really, really important. Obviously, as we just mentioned, in broadband backhaul for either fixed networks. We explained about the aggregation network needing to be there for the service layer and the optical layer, backhauling that traffic across. For 5G, it's very, very similar. The actual set of requirements are very, very similar. What you need to do in that backhaul network is almost identical. However, you need to add a few extra bells and whistles to actually make the 5G network work properly. Things like synchronization, for example, need to be very, very tightly controlled to allow all of the different mobile masts to work together. As we mentioned, this middle mile network's got to be able to cope with both new type networks where you've actually put the fiber in or you put the 5G network in. It's also got to cope with the old stuff. I mean, you would be horrified to understand how much SDH network is still in the various networks worldwide, both in service provider and in critical infrastructure. This middle mile must be able to support those old SDH services because no one's rapidly turning them off. And with these SDH services, people expect guaranteed performance, switching times of sub 50 milliseconds, good OANM. So the middle mile must be able to emulate SDH. Then if you look into critical infrastructure, so utilities, energy, defense, they really need absolutely deterministic behavior across that middle mile. They need to be able to say what the latency is, the latency variation. They need ultra high availability across that network. The way you construct that middle mile from the management layer down needs to make sure that you're at least 5 nines available, if not more, and it also must be able to guarantee the delay across the network. So you need to use special forms of routing. You can't just use the standard IP MPLS. And there are very, very many different forms you can achieve that. Then probably one of the more interesting ones we're seeing today, more and more, I say not interesting, is more prevalent, is everybody has a data center. Everything is actually going to data centers. So all of the applications, all of the services are housed in some form of data center. So not only have you got the connection to the data center, you actually, if you want to do replication or you want to share processing across multiple data centers, you have to be able to use a middle mile that's able to connect data center to data center. And that is generally ultra high capacity, normally over shorter distances. For example, in that example I gave from Surf, the distance was about 1.5 kilometers that you needed. Well, I don't know why I keep thinking 1.5. The distance is 1,600 kilometers. So relatively short if you think of the size of Europe. And they need to get the capacity as high as possible, and we were able to achieve 800 gig per wavelength. It's a pretty high capacity over a reasonable size distance. And then of course the middle mile for cable companies, MSOs, is pretty much the same as that used for broadband backhaul. It's exactly the same requirement. They're delivering services to end users. In the case of cable codes, they're using DOCSIS or fiber to the home. It depends where they are in their evolution journey, and they're trying to apply services from the core of the network. Pretty much the same. So that pretty much really is a whistle-stop tour across some hugely complex areas around IP and optical transceivers, and why coherent routing is a fundamental building block to the middle mile, and why the middle mile is important to all network operators, and actually anyone offering an application or a new service. The middle mile and having the right middle mile is key to A, the operator offering good broadband, and B, for anyone offering an application and service, they need to know that the network can actually transport data in a way that meets the performance requirements of the service. I mean, another simple example of that would be e-health. Now, if you're actually monitoring somebody's health and well-being, you need to be able to be absolutely certain it's a high availability connection. Then you need to have moderately low latency. Sub-milliseconds doesn't really matter, but it certainly needs not to be a huge amount of time. And it needs to be a very, very secure network. So that's another example of a sort of network which has different requirements again. So as I said, things to take away from this: the middle mile is the next thing that's most important now that access is happening. And it's key both for the end user in terms of good capacity, and secondly, for the service, people offering services, to make sure that they're able to get the performance they need from the network. So thank you very much for listening to that really rapid call presentation from myself. If you want to contact me, my email is here, or our local representative at Innovation Marketing is Mr. Richard Horton. His email address is here. Or if you want to look at more about Ribbon, I've given our website URL here.